Hi. So today we're going to be talking through Module 6, Lecture 1. Have that pulled up online. So we have Module 6, Lecture 1. So this is just going to be walking through this module, two other types of regression models. And then Module 7 is going to be the same kind of thing. I'm not actually as concerned with your knowledge here. I just want to give you some exposure. I think up until this point in the class, those are things that I kind of expect you to know. Here on, this is kind of like lagniappe, and I can give you a few basic tools to do things related to this, but it's mainly kind of understanding and interpreting results. So we're going to be looking at logistic regression in this module. So we talked about regular regression last time, so linear regression and also multivariable linear regression. So that's for continuous data. So say I want to predict sodium levels, or I want to predict BMI or things like that. Logistic regression is predicting a binary outcome. So a binary would be like, yes, no, did this person die? Yes, no, did this person get cancer? Yes, no, did this person have a recovery from their cancer? So it's a yes, no thing. So as an example, let's say we want to model the probability that a male weighs over 200 pounds as a function of their height and whether or not they're from New Orleans. So we'll define yi is equal to 1 if a person weighs over 200 and y equals 0 otherwise. So just recalling the examples we've used, xi, 1i is going to be the height of individual I, and x2i is going to be an indicator. So it's going to be 1 if person lives in New Orleans and a 0 otherwise. So we want to model the probability that yi equals 1. So the probability they weigh over 200 pounds based on their height and whether or not they live from New Orleans. So these will be used in the regression models, similar as linear regression. If you use a regression model, you could get predicted probabilities that are bigger than 1 or smaller than 0. So if you're modeling these 0-1 events, you could totally get predicted probabilities of 110% or -1%. That doesn't make any sense. So we're going to model this probability in a little bit different way to actually do this and keep probabilities constrained to be what they should be. So we model it like this. We're going to model the log. This is called the odds. So it's the log of the probability of the event over 1 minus the probability of the event is equal to, you'll notice this right-hand side, this looks a lot like linear regression. So it'd be beta 0, that's your intercept, plus x1i beta 1 plus x2i beta 2. So this right side looks a lot like linear regression. And if you transform this, right, so if you just did some math and worked around for probability of y equals 1, this is the format here. So there's no error terms since this comes from the binomial distribution that's from module 1. Remember, the binomial distribution is talking about n flips with probability p heads, and it's a probability between 0 and 1 like we want. So we can do a regression, a logistic regression, and what we end up getting is we get similar stuff from the linear regression. So this is just the regression results. This is the summary of it, right? So I passed a, just so everybody understands. So the syntax, right, is going to be GLM is the syntax, and I'll go over this later. Family equals binomial. And if I call this thing, so this is a formula. So this is that, y tilde x, basically. If I call this thing M1, then summary of M1 like this is going to give me the quantities that they have on the screen. So it's going to give me the summaries of what's going on. So here I get an overall parameter estimate. This is for beta 1 hat and beta 2 hat. If I want to get an odds ratio, so you would exponentiate these. So it'd be e to the 0.7. I also get a p-value for testing whether they're equal to 0. So this first p-value is testing whether beta 1 equals 0, which means height does not impact your risk of weighing over 200 pounds. And the second p-value is the p-value for testing whether New Orleans impacts your risk of being over 200 pounds. And our interpretation here is we see that increased height does significantly change the risk of being over 200 pounds. And because this coefficient is positive, that means increased height increases your risk of being over 200 pounds. Here, this New Orleans effect is not significant. So we can say the data suggests that New Orleans, being from New Orleans, does not affect whether or not you're over 200 pounds. So again, these coefficients here, they're called log odds ratios, and you can exponentiate them and show these. These are what a lot of people will report in literature. So the exponentiation of this E, and that the E code, they'll do E to this, and that'll be an odds ratio. And that's what's reported in a lot of papers. So as a logistic regression, we get these estimates, right? So I have my beta 0 hat is -57, my beta 1 is 0.7, my beta 2 is 0.98. So I can really just replace the model here. Here I've got this hat. This is a hat. Why do we have hats on things? It's hats because it's based on our certain data set. So this hat is based on our data set. It's the probability of yi equals 1, conditional on x1i and x2i. And this is the formula. So you'll just plug in your number into this and you'll get a probability. So if I plug in a person 84-inch tall from New Orleans, that means x1i is 84, x2i is 1. So I'm plugging an 84 right here, an 84 right here, a 1 here, and a 1 here. And then if I do the math, I end up getting that this fraction here goes to 0.94. Similarly, if I want to get the estimated probability of somebody who's 84-inch tall not from New Orleans, I plug in x1i is 84, x2i is 0. So I plug in 84 here, a 0 here, and then fill it out. So simple logistic regression. What's going on? Let's just think about this. So with just one covariate, remember we talked about last time multiple linear regression versus linear regression. Simple linear regression is one covariate, multiple is multiple covariates. So we're just going to illustrate this in simple linear regression and use that to give you intuition about other case. So if we had just one covariate X, this is what our probability would look like. And then we'd find the beta 0 hat and the beta 1 hats that are based on the data. And it's just like in linear regression, we optimize some functions in terms of beta 0 and beta 1. So in linear regression, right, we have to minimize this function. So we find the beta 0 hat and the beta 1 hat that minimizes this function in simple linear regression. In logistic regression, in simple logistic regression, we find the beta 0, 1, beta 1 hat that maximizes this equation here. This is a product from I equals 1 to n. So this is a product over every individual. Yi is 1 or yi is 0. So, you know, this is that product. So you basically compute this for every beta. I give you a beta 0 and beta 1, and you could compute this, this formula here for every individual and get a number and multiply them all together. And I can do the same thing. I can give you another beta 0 and beta 1. You do the exact same thing. Basically, what we want to do is do that repeatedly until we find the beta 0 and the beta 1 that maximize this function. So all you need to know is this is a likelihood function, and we are maximizing the likelihood function here for logistic regression. When we talk about Poisson regression, we have a different likelihood function that we maximize. But iteratively behind the scenes, all you need to know, you don't need to know like the theory, you just need to know that there is this likelihood function. This likelihood function is based on probability. And when we maximize these parameters in this likelihood function, we get special properties that we can use. So this goes on in pretty much everything from the rest of the semester. And in fact, in linear regression, this is also going on under the scenes. So these things are called maximum likelihood estimators, beta 0 hat and beta 1 hat. They have a lot of really nice properties. Let's say we want to test the null hypothesis beta 1 equals B, and B here could be 0. Then beta 1 hat over the standard error of beta 1 hat approaches a normal distribution minus this, if the null is true. And we can use this for hypothesis testings, and we can use confidence intervals. Now I have a note here, right? Anytime you get more data, your beta 1 hat are going to change because that's based on your data. So all this is saying, going back to say, is you see this output here, I can get this Z value by simply dividing 0.7 by 0.11. It comes out to be about this, and then compare that to a normal distribution. So it's one of the very nice things that come out of general linear models is what they're called. And these are MLEs, maximum likelihood estimates. Okay, so let's look at a data set. This is going to be an example data set. It's called the Titanic data. So it's from the Titanic data set. So I load it, I do install.packages, and I load it. And then I'm going to use library. So here I do library Titanic, and then I need to pull this data set Titanic train, which is a subset of the data. And the data is Titanic train. So I pull this in, you can see here, this is my code. I read in the data, library Titanic, that's the file. I load in the data set, it's data Titanic train. And then I say capital D data is equal to Titanic train. So now I have all my data in this data command. And again, I recommend being consistent here. That way your code will work. Like if you use data with a capital D and lowercase ATA, that's fine. Just use that consistently throughout your homeworks. It'll just make it easier. So this is what the data set looks like. I've got passenger IDs here. I've got zeros and ones, whether they live. I have their class. My guess here is higher class is more expensive. I have their names. I have their gender, their birth sex. I have their age here. Bsph, I think this is a value that means, do they have any siblings? Park is, do they have any parents? This is their actual ticket number. This is their price of their ticket. This is their cabin location. And then this is how they embarked the boat. So first thing I can do is just look at missing. I have a lot of missing ages. Just kind of walk through it. And I'm going to use this function GLM here. So this is your first introduction of GLM. Actually, you can use linear regression using the GLM function. So that's to say, right, you can go back to your last homework, and if you replace LM anywhere you have it with GLM, the code should work exactly the same. GLM, usually you have an argument for what kind of family you want. If you want linear regression, you say Gaussian. If you don't give it anything, then it will automatically work. Here we're going to be using family equals binomial. So here I have my formula. Here it says, you see it says family up here. So family is the error distribution. Here you're only going to be using a couple choices. For us, you're going to be using Gaussian. That would be for linear regression. Binomial would be for logistic regression, and Poisson for Poisson regression. That's it. That's all we're going to be using in this class. There's other choices too, but this kind of gives you a introduction to that. So if you learn, if you learn this well, you can do any other kind of regression using this function for the most part. So here I'm going to do the math here. First, I'm going to plot age by survival. Yes, no. Here's my main title. Here's my X label. Here's my Y label. That's coming over here. You can see, right, it's the data, ones and zeros, whether you survived. It's ones and zeros. So they're either stacking up here on the ones or they're stacking up here on the zeros. I'm actually plotting my line fit here. You can see definitely a decreasing chance of survival with age. How am I actually going to get that plot? Well, I'm going to get that plot this way. I'm going to create a new object called M1, and I'm going to say, okay, GLM, it's going to be the survival, who survived, data survived, as a function of data age, and my family is equal to binomial. I have to add that here. And if I do summary, these are the things that I get down at the bottom. Now, again, what do I get here? I get a estimate for beta 0, that's my intercept, an estimate for beta 1, that's my age effect. I can see here from the p-value. This p-value is testing whether age impacts your survivor chance at all. The assumption, the null hypothesis, is that it doesn't. It's independent. This p-value is significant, so we reject the null that age does not impact whether or not you survived in the Titanic. And since this is negative, what that means is increase age, decrease your chance of survival in the pandemic. This plot here, you don't really have to worry about how to add this, but basically it's using this predict function. This predict function, you actually feed in a model. So you'll save a model, and then you have to feed in a new data frame. So this is just plotting everything here. And you can see, right, that it does decrease. It does decrease as age goes up. Okay, so I want to talk about odds ratios here. So the odds of survival given some age is the exponent of this. That's just the definition. Odds is just the probability of an event over probability of not the event. That's this here. So if I want the odds ratio for increasing age by 1, I would just put x plus 1 in the top and x on the bottom like this, and I end up getting e to the beta 1. So what that means is this estimate here, when you exponentiate it, so e to the negative 0.01, that is the odds ratio. So that's the increase in the odds of death given a 1 unit increase in age, and that's holding everything else constant. So that's the definition of an odds ratio. So when you hear an odds ratio and they're talking about treatment versus death, that's just saying, okay, what's your odds of death given you got the treatment versus not? Odds ratios, we talked about them a little bit in module 3, expressing association between two binary variables, x and y. E to the beta 1 is the odd ratio for increasing xi by 1. You could try out some contingency tables here to look at. E to the beta 1 hat in logistic regression, this is our theta hat. And if we want to get a confidence interval for our odds ratio, log of theta, we need to get a confidence interval for beta 1 and then exponentiate it. So how do I do that? If I do x with M1 $ coefficients, I'm just grabbing the coefficients there. So my odds ratio here, this is 0.98. And if I want a confidence interval, I can just do confident M1 and then pass an exponent around it. So my confidence interval, my 95% confidence interval was between 0.978 and 0.999. So again, this is interpreted as the odds ratio increase for 1 year. Here, okay, the p-value for testing beta 1 equals 0 is 0.039, which is less than 0.05, right? So you know that age is a significant predictor of survival. And then you look at the coefficient magnitude. Since beta 1 hat is negative 0.01, that means increasing age was associated with decrease in the odds of survival. And that makes sense, right? If you remember Titanic, they did mothers and children first. So they did younger people. If you're a mom, you're probably younger. If you're a kid, you are. So that age effect we're seeing is a real thing. This confidence interval here, this is that estimate for the odds ratio. And the confidence interval, you just do the exponent of the confidence interval of your object. The odds of survival are 0.8989 times lower for someone who's 51 compared to somebody who's 50. And it's the same for 21 versus 20. That's the interpretation. Your odds of survival are blank X lower, given a 1 year increase in age. What about passenger class? Well, we can add that into here. Here I'm changing my code. Now it's M1 is equal to GLM. I've got data survive, as dot factor, data P class, and family binomial. I'm taking the summary of M1. So here this is, whether or not this indicates that passengers in the second or third class were less likely to survive. Why is that? Here, this is the second class here. So first class, I guess, actually is the richest class. In this case, this is second class, and we're comparing it to first class. You can see that compared to first class, second class was a significant impact. So was third class compared to class 1, right? Because we don't have a variable here for class 1. This as dot factor is going to create 2 dummy variables. Now, if I go and I look at these estimates are both negative, which means being in class 3 versus class 1 or class 2 versus class 1 significantly increase your risk of death on the Titanic. And that makes sense. That happened in the movie Titanic. If you remember the movie, all the rich people got off right away, and it was kind of a fight to the death after that. So if I want to do an odds ratio again, right, I'll do this exponent of M1 coefficients. This will give me my odds ratio. So the interpretation here is a little bit different without continuous variables. What this is saying is your odds of death, given you're in class 2 versus class 1, your odds of survival here. We're trying to predict survival, data survive. Your odds of survival in class 2 are about 50% of those that being in class 1. And the 95% confidence interval is 0.35 to 0.78. So at most, right, it's definitely at least 20% lower chances of survival in the second class, because that 20% is outside of this range here. And in the third class, right, if I exponentiate this is saying your odds of survival in the third class were about 1/5 of that in the first class. And this 95% confidence interval goes between 0.13 and 0.26. So your odds of survival here, the data suggests at least, if you're in the third class compared to the third class, are at least, or at most 1/3. They're way below that. So 0.19 is your ratio. So you are almost 5 times more likely to die in the third class than you are in the first class. And you can see that here I did X as a table, P class by survive. And this is just, you could use prop.table here, but you can see 63% of those in the first class lived compared to 47% in the second class, compared to 24% in the third class. So quite a bit fewer people lived in third class compared to first and second. And you can actually plot this. Don't really worry about this as much. I'm just showing you graphically that these are different, and you can see they are, right? So class 1, this is the rate, goes up quite a bit in class 2, and then class 3. So actually, these should line up right here. It's a bad slide. It should be here, here, and here. Ignore this slide. Okay, so multivariable logistic regression. So just like in linear regression, we could use one variable or multiples. What if we included the gender of the passenger? So this is their sex in the data set. What if we include how many sibling spouses they had? That's Bsph. What if we included how many parents' children they had, which is Parch? Before we do anything, let's look at the variables. So if I look at sex, most of the people are male, about 314 females. If I look at Parch, that's looking at parents and children. See, most people have 0 parents or kids, or they have, 1 or more. And as far as siblings, I see kind of the same thing, siblings slash spouses. Most people have 0 to 1, either siblings slash spouses. So probably a bunch of married people or a bunch of single people. Otherwise, right, they have more than that. So let's treat these as continuous variables. So I'm fully feeding these in. I'm doing a whole logistic regression here now. I'm including passenger class again. I'm including their sex. I'm including their age. I'm including their number of parents and kids and their number of siblings. So you can see that all here, and it's all fed into this one formula, and its family is binomial. So here you can see this blue at the top. This is the formula I use to actually do that. And then I take the summary. So if I start looking at the data, what am I seeing still? Well, I see a lot of, big asterisks over here. So I can see that compared to first class, still second class has a decreased risk of survival significantly, because this is a negative coefficient. Compared to first class, third class has a significantly decreased risk of survival or chance of survival. You can see that here. Compared to females, males, you see that's how it says male here, chose a level, has a significant decreased chance of survival. You see that here. Increased age, every year that you increase in age, your chances of survival go down significantly. Having parents or kids did not affect your risk of survival. And having increased number of siblings so it's what, siblings or spouses, increased number of siblings or spouses, decrease your risk of survival, your chance of survival. So you can see here, this is significant, and it does decrease that survival chance. So I just looked at this, I looked at siblings and then whether or not they lived. And looked at about 34% of the people that had no siblings or spouses lived, compared to 53% that had one. And then it goes down quite a bit after. So the difference we might be seeing is out of these people that had 5 or 8 siblings, that was 12 people and none of them survived. So maybe that's bringing kind of our overall effect down. So let's change up the variables a little bit. So instead of looking at just sibling and spouse number as a continuous number, let's just say, do they have any siblings or spouses at all? Same thing with parents or kids. Do they have any parents or children at all? So what I'm going to do, all I'm going to change is I'm just going to put in parentheses here, because I'm transforming this variable into a logical statement. This will be a logical true if this condition is true. Otherwise, it'll be false. And then I have my data Bsph as well, greater than 0. So now I've just turned this into a binary variable. So if I look at the results now, what do I see in the bottom? I see that the number of parents and kids and the number of siblings and spouses now is not significant. You can see these p-values are bigger than 0.05. The rest of the results don't change, right? Increased age decreases your chance of survival. Being a male decreases your chance of survival, and being in classes 2 or 3 decreases your survival compared to class 1. If I want to get a confidence interval here, I can just say, okay, look, I'm going to bind these together. This is the exponent of M1 coefficients. That's this right here. And then I can do X with confidence. So that's just putting everything together. You don't have to do it like this, but I can see right here that age, if age is significant, then the resulting odds ratio confidence interval will not overlap with 1 instead of 0, 1. Here you see that's the case. You can see that parents and kids does overlap with 1, so it's not significant. Siblings and spouses does not overlap with 1, so it's not significant. Here you see that males, there's a significant increase in the risk of death. So your risk of not surviving or decreased chance of survival in males, all of that is here. How many predictors can you use? If yi equals 0 or 1 doesn't happen a lot. So if everybody on the Titanic died or everybody lived, it's kind of mixed between that. Then that limits the number of predictors you can use. One guideline is there should be about 10 outcomes for each predictor. I think in general, that's a good thing to do. Is if you have a rare outcome, you don't want to be using lots of predictors in your multivariable logistic regression. Another issue you might have is multicollinearity. So when you have explanatory variables that are highly correlated. So for example, if you feed in BMI and height, which are both very related to each other, you could be getting a problem, or weight in BMI, you could be getting an issue. And basically what it will look like is it'll look like both of those variables will split the effect on the outcome because they're both so closely related. Another issue that you might have is called separation. So separation is like a weird problem in statistics. So it'd be like, imagine that I'm treating patients with treatment A and B, and 100% of the patients in treatment A got better compared to 40% in B. Well, that's called separation. And visually, you can imagine an x-axis. So here I've got a continuous variable, and you see, right, I'm getting all zeros, and then at a certain point, I get all ones. So if you feed this into a logistic regression, you're going to get a weird odds ratio. It just comes out weird. I don't know why. It's just a problem with logistic regression. It assumes randomness, I guess, and this is essentially a non-random thing. So if you ever, I just point this out because it's something you should be aware of. If you ever run a regression, you get some weird estimates. What you might want to say, like, for example, if the male estimate is infinity, you might want to check, well, what's the rate of death in males versus females? Because if it's 100 versus 40 or 0 versus 40 or whatever it is, that might be causing your issue. So this is just an example of what this looks like. So this is a data set, right? So here I've got a data set. It goes from 1 to 20. And if X is bigger than 10, Y is going to be 1 by default. So it actually looks like this. X just goes up and then it jumps across. And I actually fit the data here, Y again, X, family is binomial. And you can see here, this estimate here is really large one, and this standard error is ginormous. So this is an example where you have problems with separation. The standard error here blows up. So if you see some weird results, you can usually look, if this thing is bigger than even like 10, I think, or 20, then this thing is too big. This thing here is 25,000. So it's enormous. And that's a byproduct of intentionally going to separation, right? Because you can see the Y values for X is equal to 1 is 0, 0 for 2, all the way up to 10 is 0, and then 11 on it goes up to 1. Multinomial logistic regression is something else you might want to be aware of. I'm not going to quiz you on this, but it's just something you can be aware of. Instead of predicting yes, no, did they survive, you're going to predict more than two categories. So for example, maybe you want to know, do alligators eat mostly fish, invertebrates, or mammals? You might go and find a bunch of dead alligators and see which one they eat the most of. And you might say, okay, does this pattern on their back influence whether they're going to eat mammals more than fish, et cetera, et cetera. Multinomial logistic regression is a good way to do this. If you want to predict cancer stage 1, 2, 3, 4, this is a good way to do this as well. You also might hear of ordinal logistic regression, which is probably more appropriate for ordinal categories like cancer stage 1, 2, 3, 4. But you can do these with multinomial logistic regression. So just be aware of that. Let's go look at the homework real quick, just so we can kind of tease through it real quick. Okay, so here I have the homework. I definitely revamped it recently. I made it a little bit easier. So what you need to do is you have this data set, cancer treatment survival, which I should have given you already. It's on here. I have treatment is equal to 1 if somebody is given a novel treatment, otherwise 0. I have their age, I have their Charleston comorbidity index. It's just a score. The higher the score, the worse off the patient is. I have male identity, that's equal to 1 if somebody identifies as male. I have smoking, which is equal to 1 if somebody has smoking. I have cancer stage. I have whether or not they died within 500 days and how long they've been around and whether or not they have advanced cancer. So I want you to answer the following questions. The first one is perform simple linear regression, logistic regression to predict death. So just death itself based on age. So syntax wise, right? I don't know what this variable looks like, but you've got data. Let's say it would be GLM, call this thing M1 equals GLM, data, death, data, age, and then I've got to do a family equals binomial. So I'm not sure that that's what these variables look like, but that's basically the syntax. And then if you want to look and see, well, how do the results change? You do summary of M1 after reading this file in. So what did the results say? How does age affect the outcome? Now remember, what you're going to be looking for is in these summaries, so in the summary output, the first thing you're going to do is look for these p-values. If that p-value is significant, then you're going to look at the estimate. If the estimate is positive, that would mean that it increases your risk of death. If the estimate is negative, that would mean that it decreases your risk of death. Perform a chi-squared test of independence for advanced stage cancer and death. Are these factors associated? So remember, this is using chi-squared tests. You've already done this before. The third question is you perform a multiple logistic regression to predict death as a function of treatment, age, CCI, male identity, and smoking status. So you'll put a whole bunch of variables in here. You'll have treatment, age, CCI, male gender, and smoking status. Smoking here, that's up here. Which covariates are expensive or are significant? Which ones aren't? And again, what you'll do is you'll go look at all of these together. Okay, here I see height is significant, but not New Orleans. Height has a positive coefficient, so it significantly increases your risk. New Orleans doesn't do anything. Plot a scatter plot of age and CCI using a correlation test. Is there a significant association? So you can remember core.test from the last class. And then the last question will be perform multiple linear regression to predict CCI based on treatment, age, male identity, and smoking status. Which covariates are significant? And that's the whole assignment for here.